we're going to start chapter 2, and this is just a little about how you, in mathematics, how you develop things. And you always start the axiomatic method, and you have undefined terms. So you define terms, if you read in the text, if you look in the dictionary, a defined term is really a circular thing. You look up the definition of something, then you look up the definition of what element is in what's described, and it'll bring you right back to where you started from. That's a defined term. So basically you start out with an undefined term, then you have definitions, postulates, and axioms, which are defined, and then certain basic assumptions you have. Now, then you develop theorems based upon that. And if you change any of the postulates, axioms, or definitions, then the system changes. So we're going to develop then the system of geometry, Euclidean geometry, in this section. The undefined terms that they specify then are points, line, and a plane. And a point is just the concept of something that has no dimension to it. It's just, and then a line is just a series of points that has no, it has no dimension to it, no size, nothing to it. It's just a line. And then a plane is just a series of all the dots and lines. So those are just undefined terms that you empirically visualize. Then space comes from the definition of those undefined terms. Space is just all the points that exist, and then it's all the accumulation of all the lines. And then postulates is what do you then assume to be true with all of those things. And we're going to go through and develop postulates in the next part. And once you have the postulates with the definition in the undefined terms, then you develop theorems based upon those. And theorems then are the things that you can prove to be true. Now the first postulate that they put forward on page 40 is every line contains at least two distinct points. And then the second postulate is 2 points contained in one and only one line. So, and then the third postulate, 2 lines, if 2 lines are in a plane, then the line containing these points is also in the plane. So this is postulate is like a definition using the undefined terms. There's collinear points. That means that they all fall on the same line. They're collinear. Non-collinear, they don't fall on the same line. Now a line is assumed to be if you have 2 points, it's all the points just stretch tight. A line does not have a circular shape to it. It's a straight line. And then postulate 4 says 3 non-collinear points are contained in one and only one plane. Every plane consists then of 3 non-collinear points, at least that. Points that lay in the same plane are called coplanar, just like points that lay on the same line are collinear. And non-collinear then don't lay on the same plane. In space then, it requires 4 points that are non-coplanar to make up space. And then the postulate 6 there on the next page is the ruler postulate. Every line can be made into an exact copy of the real number line using a one-to-one correspondence. So every line lays out has the same number of points, and there's a one-to-one correspondence between the points on the line. So that's all that's saying. A coordinate is simply one of the, identifying one of the points on the line. Now, every line has an infinite number of points, and all lines are infinite then in length. And then you define the distance between A and B as the non-negative difference between the 2 points, the coordinates of 2 points. The line segment is just a part of the line, and usually it has designated endpoints, whatever they are. It could be AB, it could be X, Y, whatever it is. Those are the endpoints of the line segment. Now, 2 lines are congruent if they have the same length. So they don't have to have the same angle. They can be one, but the length is the same. And when you do congruence, lines, like if you have 2 lines, if you have AB, and if you have this line, and then you have CD, and the way you specify them as the same length is, you'd say they're congruent, and you have that little wavy line like this on the top. And that's just congruence. Same length. They're going to show you that they can be the same length, but they don't have to be the same direction, if you will. So if you have a line like this, where it's AB, and a line like this, and if you give me grant me a leeway that those 2 are the same length, then a lot of times what you'll do is you will designate that they are the same length by putting something like that in there, so that you can identify which lines are congruent to each other. They're going to talk about angles and their measures. Now, what they would do is they would specify an angle, and if you had B, A, C, now you would say that's an angle. Now usually what I do with angle, I would do this, B, A, C. Now that's the same as the angle C, A, B. They're the same angle, just specifying it different. Sometimes you might call it just angle A. Now, whenever you specify measure, what I'm going to use is I'm going to say the measure of angle BAC. That would be measuring it that way. Now, usually when you measure, if you have a protractor, it's going to measure the angle positive going that way. When you do azimuths, azimuth is going to measure this direction on the angle. So, and 2 different ways of measuring an angle. One is in degrees. So if you have, let's see, better than that. And if I rotate this, if that dotted line starts out down here and rotates around this way back on itself, that's 360 degrees. So 1 degree is 1/360th of 1 rotation. That's just by definition. And usually you're going to use a protractor. Now you don't have to measure the angle from a horizontal. You know, you can take something like, you can have an angle formed by those two rays, and sometimes what they'll do when they specify an angle, they might give the angle a letter down in here. Now you can specify the angle with a letter there, or you can specify the angle with, you can have it go from B to A to C in terms of line segments. You can have AB as a ray and AC as a ray with a common vertex back here at A. That's an angle. Or you can specify it as angle A, or you can specify it as angle L. So there's lots of different ways of specifying it. Now, typically if you have a protractor, you would lay it out. You lay your protractor so that 0 is there, and the one edge of the protractor laid up here, and then laid around like that. And then this would be the angle that you would measure. And you would normally measure counterclockwise.
Will we need a protractor for this class?
I don't think I'm going to be, I'm going to try to avoid having to do those kinds of things. But if they, we'll see. I mean, I haven't gone through this book once, so I don't know quite what. As I looked at it, I just don't see that we need it, and I don't think I'm gonna do that kind of thing. But the protractor rule says that that's the way you do it, and that's the way you measure angles. Because they have the postulate 2,7. If we place one ray on the angle 0 degrees on the protractor, they're just saying that there's a one-to-one correspondence, and that's how you'd lay it out. Now the definition on page 43, acute angle, this particular angle that I've drawn here would be an acute angle. Any angle that measured between 0 and 90, not 90, between the two. And so you have a 0 degree angle, you have a 90 degree angle, right angle, and then you have an acute that lays between the two. This one would be an acute. So you have acute, right, obtuse. So if I would just grant me that this is 90 degree, and usually you would specify it like this. That would indicate that that would be a 90 degree. So then the angle that's out here that's formed, let's see, let's go. The angle CAD, that's obtuse.
Anything over 90, what's the upper limit?
Above 90, less than 180. And then there's a straight angle, and that's going to be an angle right out here. That's 180. So if I did the angle CAE, that's a straight angle. And that's 180 degrees. So a right is 90 degrees. Acute's between 0 degrees and 90. 180 is a straight, and then obtuse is between 90 and 180. Don't include 90 and 180. It's between the two. And then if you have an angle out here, and you specify it this way. This is a reflex angle. Now, the only time that you'll say a reflex angle is that when it is specified. Because normally if you have an angle that is F, that is angle CAF, reflex, when specified like the green. But if you, typically what you would do is when you have a reflex angle, you would measure it this way. And then, see, because any angle could be reflex, you could have this one or this one where this is 90 degrees, and if you measured any of those from here, they're all reflex angles. But when you measure them this way, then that's an acute, that's a right, and that's an obtuse. So usually you don't, you measure them acute, right, and obtuse.
Is there a right way to measure it, or you just measure it the way you want? Is it?
A right angle always has 90 degrees in it.
I mean, the measurement, is it counterclockwise or just
Well,
clockwise?
you can measure, this would be a reflex angle, you would measure it counterclockwise and specify it either as acute right or obtuse or straight angle. Straight angle, either way, would be the same, yeah.
So that bottom right would not be calculated at 270 degrees?
No, you would,
Okay.
you would typically, if, when you're, no, just a second, Vince. You can call it 270 degrees if you want to measure it as a reflex angle. Typically, when you're specifying it, because that 270 degree angle, if you specified it measured clockwise, you'd have to call it a reflex angle, because there's no designation for a 270 degree
Okay.
angle. You'd have to go back and say from counterclockwise and call it a right angle.
Gotcha.
You
So
know,
anything between 180 and to the 360 gets to
360.
be a reflex angle?
Would be a reflex angle. So if you want to specify it as a right, you're going to have to measure counterclockwise. So then that's how come it's, because you don't, see, you don't have an angle that's between 180 and 270, you don't have a name for it, other than reflex.
Okay.
And a 270 angle, you only have a reflex angle when you're beyond 180. And, you know, for one that's back in that, 270 to 360, it's only a reflex angle. So when you're specifying it, acute, right, and obtuse, you have to come counterclockwise in order to specify it. That's what typically they do. Because then you can specify them in terms of an acute, right, obtuse, or straight angle. But the straight angle, there's no problem going clockwise, counterclockwise, or clockwise. They're both straights. And then the right angles, what you have to have to be right angles. The lines have to be perpendicular. Now typically you're going to specify lines like you'll call this one L and this one M. And then L has to be perpendicular to M. And those lines really are, because they have no endpoints, they're really just this kind of thing. And then what I'm doing is I'm saying that those are perpendicular. And that's what, then you'd specify it this way. You could have a designated line where you'd call this one AB and this one CD. And you know, you could say even, you could say it anyway. You could say AB like this, and that would be equivalent to saying line F, right? And then you could say CD and draw an arrow both ways, and that's equivalent to saying line M. Or you could say AB, that line segment is perpendicular to the line segment CD. Then you're just taking those segments. I mean, you can specify a lot of different things. This would be line segments. This would be an entire line, like these two would be entire lines. Then you could also designate rays, and if you designated them, you could say A, B, that ray, and that would start here at A, go to B and go through it, is perpendicular to the ray CD. And that would just be say that you're going from here out this way, you're going from here down this way. You can specify them perpendicular, if they are. So there's lots of ways that you can do things. Now, when two angles, on the next page it says when the two angles have the same measure, then the angles are congruent. And once again, you do not have to have, if you grant me a little bit of leeway, there you go. And you see, if I did something like this, that would indicate the measure of those two are the same. And then if I designated this as L and this as M, then the measure of L equals the measure of M, and therefore the angle L is congruent to the angle M. I guess I do it this way, angle L. When their measures are the same, then, and probably to be more specific in terms of writing this out, what I should say is the measure of angle M. Then if the measures are equal, then the angles are congruent, because they have the definition. You couldn't, I mean, it wouldn't be a proper notation to say something like this: the measure of angle L is congruent to the measure of angle M. The definition is they're congruent if their measures are the same. So if the measures are the same, then you can say the angles are congruent. It's kind of a technical thing, but that's. Now, complementary angles, it's probably pretty familiar to you that those are angles whose the sum of their measures are 90 degrees. And supplements are, the sum of their angles are 180. Now, the angles do not have to be adjacent to be complementary or supplementary. But if you do have adjacent angles, then adjacent angles would be angles, and I'll just write them out as rays. Those two angles are adjacent because they share the same vertice and they share a common side. They're not they're not measures equal, they're just adjacent. So you can have congruent angles that are adjacent or non-congruent angles that are adjacent. Congruent angles that are complements or congruent angles that are supplements, or but they don't have to be adjacent to be any of complements or supplements. Okay, on page 46, they're going to show you let's see, what do they call it? It's a compass. And notice that that compass is telling you 32 equally spaced directions on the compass card. And if you divide 32 into 360, the distance between each one of those compass headings is 11.25 degrees because they're equally spaced. And ships will run compass headings. Airplanes run compass heading. It isn't used as much anymore with the advent of GPS, but you should learn how to do it, because if your GPS goes out, then you're gonna be relying on compass headings. The interesting thing which I never thought about as I read through that, a camera is always set up on a tripod, and I surveyed and never really thought about it, but you always have a tripod underneath a level or something like that, and it's a plane. I mean, 3 points are in a plane, so you're establishing a plane however those tripod points of that tripod are. When you're in some plane. Now you can go above that plane and extend your legs so that you run a parallel line to the segment of the earth that you go by, but you're running it off of a plane. The plane isn't, doesn't have to be parallel to your, because when you set an instrument up, you're always setting the instrument 3 points down, establishing a plane, and then you're leveling the instrument. So the instrument is parallel to the ground, not the plane that the tripod points off of.
Not always level to the ground. You may be on a hill.
You're always level to the ground. I mean, level to the surface of the earth on that segment of the earth that you're, yeah. Terminology, you're right. But it's a plane that you're setting the tripod.
A form of construction where you're
Yeah. Okay. Number 2 in a set of problems. How many different line segments have B as one of the endpoints? Name them. So there it has. Okay. So this one's A, B, E. So how many different line segments has B as an endpoint? Well, you could start out with AB comes in. That's a line segment. Then you could go BC, BD, B, E. Every one of those has B as an endpoint. Are there any other ones? I mean, the thing there is B has to be one of the endpoints.
Couldn't it be B infinity or B negative infinity?
Line segment. So it doesn't say ray. If it said how many different rays, then, you know, but then what you do is you would have BA ray, and then you'd have BC ray, and all the other ones would be on that same ray, BC. BD, BE would all be on the ray, same ray. But line segments, there's that many line segments. So that it's kind of 4 then, so we'll give it away. It says how many different rays have C as the initial point.
Just 2 then.
Technically there's 2, I think, but so it'd be CA and then CE. Now, it depends upon how, if they wanted to do it the way they're saying, how many different designation of rays are there that have C as an endpoint?
CD is the same thing as CE.
Yeah, you do CD and CB. That's the way I think the problem should be worded, to have 4 of them. But they have 4 worded the way they have, how many different rays have C as an initial point. Well, as far as I'm concerned, there's only 2 rays. But there's 4 different designation of rays. So 6, it says name the ray AEA in 3 other ways.
It's just what we just discussed.
Yeah. So you could name it as what?
ED, EC, ED.
ED, EC, and EB. See, and I think when they do that, that makes the way they worded 4, that there's 2 rays, not 4. That's as far as I'm concerned. Okay, any questions on that? No, just as sure as we discuss it, I put something on a test or a quiz, and you will say, oh, well, that isn't the way you told us. Okay, number 8 says points A, B, C, and D are located on line L. Their corresponding coordinates are given. Find each of the following distances. So it's that thing down below. So let's see. So they're giving, and I'm not going to draw out the number line. I'm just going to draw the points and establish their coordinates. This one is called A. This is called B. This is called C and D. And then they say A is -5 square root of 2. B is the square root of 2 negative. C is the square root of 2. And this is 4 square root of 2. So that's the coordinates on that number line. And then they're saying find the distances. So now when they're doing this, they have AC. Now, to me, I would prefer, if I did that, AC. This is AC line segment. I think that's clearer, because AC makes me a little nervous when it's not. But the measure of AC line segment, I think, really specifies. That's what, so that's what you have to see if I do it. But anyway, what it's going to be is it's going to be the absolute value of the difference of the coordinates, right? Minus 5 square root of 2 minus the square root of 2.
Is that minus 5 on your ray? I thought it was minus 3.
Did I put it, was that 3?
It could be 5. My eyes are not what they most.
Oh, 8. I think it says A is a minus 5 square root of 2 in the book. This is supposed to be a 5. The book says it's a 5. So, what is this then? The absolute value of a minus 6 square root of 2, right? Because you subtract the 2 coordinates, right? Which is 6 square root of 2. Then the BD, so it's a measure of E line segments. So that's going to be the absolute value of minus the square root of 2 minus 4 square root of 2, which is absolute value. Let's go down. Absolute value of negative 5 square root of 2, which is 5 square root of 2. And then BC, which is the measure line segment BC, absolute value of minus the square root of 2 minus the square root of 2, which is minus 2 square roots of 2, which is 2 square roots of 2.
Professor, you were looking for distance. The distance formula, wouldn't it just be 2 and drop the radical?
No, it'd be 2 square roots of 2. Because, you know, what you're trying to, I don't know what you're trying to do. If you multiply square root of 2 times square root of 2, it's 2. But if you're adding or subtracting them, it's 2 times that, right? So if you add 3 and 3, what is it? 2 times 3. You got 2 3s. Here you got 2 square roots of 2. Both with the same direction. And the last one is 80. So it's the measure of AD. So it's a minus 5 square roots of 2, and then minus 4 square roots of 2. They never gave us AB, did they? So this is going to be minus 9 square roots of 2, which is 9 square roots of 2. I'm just going to show you, if you have AB, that's a measure of AB, and that would be minus 5 square roots of 2 minus a minus square root of 2. which is gonna be minus 5 square root of 2 plus square root of 2. And that's gonna be 4 square root of 2. Okay. Oh, man.